my IGCSE. Hello. So oh my goodness, we've got 3 lessons left of astronomy, and then I've gone through the whole of the IGCSE physics course for home educators in this format. So we're doing the life cycle of stars. It's a nice kind of standalone lesson, but it does bring in a lot of different things that we've learned from throughout the course. So I'll start off with how stars burst into life. A lot of this you've heard before if you've been to previous lessons. So, apologies for the fun reflection. You can see me as well. Hello. So hopefully this isn't news for you because he came a couple of weeks ago. A cloud of gas and dust in space is called a nebula. This is just awful, isn't it, this reflection? It's so bad. Is it better if I do that? Not really. Yeah, space isn't completely empty. Welcome if you're just joining us live. We've just got started. Space is not completely empty. There is gas and dust floating around. It's mainly hydrogen gas, and you call that a nebula. Here's my little diagram of a nebula. Now, we've looked at this before. Even the teeniest little particles have got a gravitational field around them. So these tiny little particles get attracted to each other because of gravity. So they pull towards each other. What does this do? What happens to particles when they get closer together? Well, you get more collisions. They bump into each other more, so the temperature rises. I'm going to test you on this in a little bit. They didn't do very well on Facebook. I'm expecting you to do better. Okay, so we've got this cloud of mainly hydrogen gas, but some other bits and bobs. Because of every bit of matter having gravity, they've pulled towards each other, so they get hotter. And this collection now of sort of denser particles, this is a protostar. Not quite a star, but a protostar. Something else has got to happen for this protostar to become a star. This hot ball of gas, what happens? What does happen? You know what happens, actually, because we talked about it. The last module we did, this is Astrophysics, this is the last module. The second to last module we did was on radioactivity. Do you remember? There's something that happens inside that hot ball of gas, that hot protostar, to turn it into a star. Anyway, be thinking about that. While you're thinking about that, here's an actual photo, an image of a protostar. Well done, NASA. Here we go. This is the catchingly named L1527. It's 460 light years away. You remember we did that last week? So if light travelled for 460 years, it would get to this protostar, taken by NASA's fantastic, fairly new James Webb Telescope. So in this protostar, a solar system, a new star is about to be born, and a solar system with it. It's actually that little black band there. You see, it's just amazing, isn't it? Your human brain, your puny human brain, can't believe that this is real. The black band right in the centre there is about the size of our solar system, and this is how our solar system formed. Right. So what happens when the protostar gets hot enough? Did you say nuclear fusion? Remember, fission is particles splitting apart. This is fusion. We've talked about how fusion happens inside the sun. Here are 2 hydrogen particles. They look weird, but they've only got 1 proton, so it's definitely hydrogen. It's just there's a couple of extra neutrons in there. They start smashing together inside this protostar. They don't burn. That's just an effect that I like. But they fuse together to form helium particles, and this is what is called nuclear fusion, and we have learned that that releases a lot of energy, so much energy, and this is when a star is born. Get your bread, okay, if you're going to use bread with me. So you're all right so far. We've got a cloud of gas, mainly hydrogen, but some bits of other pieces, which is called a nebula. Because gravity, that's pulled towards each other, these little particles, and we've had a protostar, which is just a hot, denser ball of gas. And now we've got nuclear fusion happening inside the star, so that is the definition of now a star, a typical star. So we're going to talk about pressure. You got some bread here, so I've been painting in the last lesson, so my hands were a really weird colour. If you've got some bread with you, just give it a little press. It's squishy, right? You can compress it. You can make it smaller. You can apply pressure to the outside, push inwards, and it gets smaller. And then hopefully if you let go, if you haven't pushed too hard, it gets released again. Why isn't that little piece of bread collapsing in on itself? Why does it bounce back? What is it when you squeeze that bread? Why does it unsqueeze again? And why isn't it being squeezed? Why isn't it as small as it can be? you know what I mean? Let me tell you how this sort of has a bit... Let me explain why this doesn't have really anything to do with stars. We're talking about pressure. Here's some bread, right? Just a square of bread. The forces acting on the bread are equal. It's not expanding and getting bigger, and it's not compressing and getting smaller unless you push on it. So the forces on it are equal. Where are those forces coming from? Well, you know the force that's pushing on the outside, right, of your bread? Come on, you IGCSE physicists. What force is pushing on the outside of the bread? What is air pressure, right? I mean, I've just said that pressure is a force. There were previous lessons which explain why that's not right. But there are air particles pushing on this bread, like trying to push it in. Why isn't it collapsing in on itself? It's because there's a different kind of, well, there's pressure on the inside as well, pressing outwards. If you haven't got a piece of bread and marshmallow, works very well for this. And the pressure on the inside is actually also air pressure, right? There are pockets of air inside the bread. You can see them. And all that air is pushing outwards. The air on the outside in your room is pushing inwards. And those forces are balanced. The pressure is balanced. So the bread isn't moving. It's hard to find activities for star lessons, okay? Because stars don't really relate to anything in our houses. But it's the same with a star. What's the pressure pushing inwards in a star? What's the pressure trying to collapse the star? What is it? It's not pressure, it's a force. What's the force pushing on the star? What is it? It's gravity, isn't it? Yes, it is gravity. Because the star is made of matter and all matter has gravity. So yeah, gravity is trying to pull all this matter inwards. And what's the force, or what's causing this pressure on the inside to push outwards? That is the nuclear reactions, right? That are releasing a lot of energy. So the pressure in the center is caused by these nuclear reactions from the hydrogen particles fusing together to form helium particles. So I'll just put nuclear reactions, yeah? Whew, right. So that's a protostar that has turned into a real life star. And I've written it here. Pressure pushing in equals the pressure pushing outwards. So we would say that the star is in equilibrium. Nice posh physics word for all the forces on it are balanced, all the pressure's balanced. And it will be in equilibrium for quite a few billion years. I don't know why this freaks me out. Our sun is about 4.5 billion years old, so it's roughly halfway through its life. It's a long time, right? I don't know why I read that and I go, oh my goodness, we're already halfway there. It's a weird idea that one day our sun will die. We won't be there to see it. But yeah, our sun is a very average sized star, and it's we think going to burn for sort of about 10 billion years. So it's roughly halfway through its life. But eventually, the hydrogen in the star starts to run out. The hydrogen, which was the cause of the nuclear reactions, which was creating this outwards pressure, which was balancing the star. So what happens when the hydrogen runs out? Well, the pressure pushing in is greater than the inner pressure, and the star... Come on, let's play Guess What's in the Teacher's Head. That's always a fun game. If the pressure pushing inwards is greater than the inner pressure, which is pushing outwards, then the star will... I've put the star contracts. You could have said like collapses, or people on Facebook yesterday were saying shrinks. That's all right. Yes, it contracts. This means the core of the star gets something again. Come on. Ofsted would hate this. There's no teacher points for this kind of questioning. Just guess what's in my head. But come on, I gave you a massive clue earlier. What happens when the core of the star contracts? The core of the star gets something again. People on Facebook were going, gets smaller again, gets shrunk again. No, it's not another word that means contracts. What happens when particles get forced closer to each other? So there's more collisions. It gets hotter. Well done if you said that, if you picked up on my angry questioning. So it gets hotter. So you've got helium nuclei, right? Helium particles now that are in the star. They suddenly get all squished together and they get enough energy because of this gravity pushing them inwards, that they start fusing together and we get these heavier particles formed. At the same time, the outer layers of the star start to expand. This bit, I don't like this bit of the lesson because I think it's better if I explain things, then they'll stick in your head. For actually your exams, you will probably get a lot of points in your exams for just remembering the names of the stars, you know, the protostar and the sort of nebula. So let's go back to the bread. We've had our, what we call a main sequence star. I'll explain why it's called a main sequence star in the homework that I set you. But we've got this typical star in the middle of its life. It's all happy, it's all balanced. It runs out of hydrogen particles. So that means that it collapses, it shrinks, because suddenly the outer pressure is more than the pressure from the nuclear reaction. So it shrinks and shrinks and shrinks and shrinks. So this is the start of our star dying. This is not a typical average happy middle-aged star anymore. It's starting to die. Hopefully I've explained why the star shrinks. I'm not going to explain to you why at the same time the outer bit of the star gets bigger. I can't explain it, to be perfectly honest with you, because even the textbooks that I have from university, Astrophysics, don't explain it. They just go, oh, it's very complicated. But that is what happens. The core shrinks because it's running out of fuel. The outside gets bigger. What happens when things get bigger? What happens when particles are forced to expand? The outer layers of the star start to expand, so they cool down, okay? Things that are squished get hot, things that have expanded cool down. So you've suddenly got a star, flashing my bread again, with a very hot core, but the outside of it is actually quite cool. Please remember from our waves lessons how gamma rays have got the most energy, radio waves have got the least energy, and right in the middle you've got this beautiful rainbow where red light actually has the least energy of all the visible colours, and blue light has got the most energy. So what we have is something called a red giant. The outer layers of the star are cool, so they're red. You don't probably actually need to know most of that. You really just need to know that it's called a red giant, but that's why it's called a red giant. So eventually, the particles fueling the nuclear reactions run out again, and the red giant becomes even less stable. What happens? Well, two things happen at pretty much the same time. I'm hoping you can tell me one of those things. So we've had a normal medium-sized average star, helium in the middle, hydrogen in the middle, fusing into helium, and then the hydrogen runs out, so the core shrinks, and then the helium starts fusing, and you get the outside expanding, and it looks red because it's cooler, so it's a red giant. Now, the red giant's run out of helium, hasn't it? So its core gets squished even more. So here's the two things that happen to this poor red giant, which is proper in turmoil. The number one thing that happens is the core collapses. I'm just going to leave it to the NASA website to describe what happens next, because they just do a beautiful, beautiful job of it. When the core of the former red giant has exhausted all of its fuel and shed all the gas it can, the remaining dense stellar cinder is called a white dwarf. The white dwarf is considered dead because atoms inside of it no longer fuse to give the star energy. But it still shines because it is so hot. Eventually it will cool off and fade from our view. Our sun will reach this death about 8 billion years from now, right? So in 5 billion years, the sun is going to sort of stop being a nice, healthy, middle-aged star and start to die. It's going to become a red dwarf, a red giant. And about 8 billion years from now, even the red giant is going to run out of fuel, and you're just going to have this thing that NASA call a dense stellar cinder. What a beautiful, beautiful phrase. Yes, NASA. Called a white dwarf. And the second thing that happens at the same time as you get your red giant collapsing and turning into a white dwarf is the star is giving off a huge amount of gas, and this gets heated by the hot white dwarf and gives off light. Ah. Here is an actual photo NASA took of this happening 700 light years away. So we've had our red giant, remember, where the helium has been fusing to form heavier particles, and you've got that sort of cooler gas around the outside, which looks red, so it's called a red giant. It's a dying star. Now that's run out of fuel, you've got this is an actual photo. That's a white dwarf. That tiny little dot there is a white dwarf. This is a red giant dying. That's a white dwarf. The red bit around the outside is the glowing gas being given off, and the blue stuff is infrared light. So here we come to a name which I'm so sorry about. This layer of glowing gas around the white dwarf is called a planetary nebula. It doesn't have anything to do with planets. It's just that someone made a mistake 250 years ago. They thought it had something to do with planets and the name stuck. So this is what we're stuck with, okay? With apologies for everyone who has anything to do with science education. You started off with a nebula. That's the cloud of gas just hanging in space. Gets pulled together because of gravity. So you get a protostar, which gets hot and starts fusing its particles, and that is just an average mass star, right, like our sun. That runs out of fuel, the core collapses, the outside expands and gets cooler, so that's your red giant. And then it sort of looks like they happen at different times, but really it kind of happens at the same time. So the red giant collapses again because it's run out of fuel again. So you've got this really dense white dwarf with this planetary nebula around the outside. So the planetary nebula is gas that's getting heated up by the white dwarf, so it's starting to glow. Is that all right? This is a massive lesson, isn't it? There is so much in this lesson. When you come, I'm not expecting you to memorise all of this. You're just going to have to learn these words if you ever do an exam. You're going to have to revise, I'm afraid. But let's start to get this clear in our heads, shall we? If you've got a balloon with you, if you haven't, just get an imaginary balloon out of your pocket and pretend. But if you've got a balloon with you, can you talk yourself through as many stages as you can from nebula to white dwarf? So I've tried to give you some clues. Right? I want you to imagine that you're doing a lecture. Imagine that you're giving a lecture in what I just said, thinking about the very beginning, that cloud of gas and dust in space called a nebula, all the way through to a white dwarf. You've got a balloon, you're giving your mini lecture. What are you going to do? How are you going to use the balloon to explain what happens? So I've given you some clues. Are you going to start with the balloon inflated or deflated? How will it end? Will it end with the balloon being inflated or deflated? How will you show the forces acting at each stage? And here's some words I think would be good if you would use. Nebula, protostar, nuclear fusion, gravity, pressure, collisions, hot, cool, red giant, white dwarf. Go on. I'll give you a minute. Have a go. How are you doing? Shall I spin you around and show you what I ended up doing? Yeah, well. So I was thinking, I was thinking I would start with the balloon empty, because that's gas at a very low pressure, right? So the nebula, as it starts out, the cloud, the gas is obviously sort of all quite far apart, so the pressure is low. But then I thought, but it's also a bigger thing than the protostar, which comes afterwards, right, when it's shrunk. So I decided to start with a full up balloon, but you might have done something else. It doesn't matter, it just depends how you justify it. Pardon me, balloon's got a hole in. Reuse, recycle. Right, there we go. So that's my nebula floating in space, loads of different gas, all the particles reasonably far apart. And then I'm going to say that the outside of the balloon is gravity. So gravity comes along and it's not right, is it? Because there's gas escaping and it wouldn't be escaping. I would be just squeezing this and forcing the particles closer together. But I can't do that because it's a balloon. So we'll just have to pretend that now that's smaller, those particles are all closer together, more collisions, therefore hotter, and that would be a protostar. And then I guess I'm just gonna have to release a little bit more to show that now they're so close together, there's so much energy in there that nuclear fusion has begun, and now we've got a regular, what we call main sequence star, for reasons that I'll explain in your homework. So that is my main sequence star. It's an average sized star, about the same size as our sun. So that's just going to tick over nicely for, I don't know, like 10 billion years. But you imagine how much helium that is for it to just be constantly fusing together for 10 billion years. Human brain, I can't handle it. Anyway, that's what's going to happen. And now the hydrogen. Now the hydrogen is getting used up. So that inner pressure is going to reduce. So we get shrinkage, but now actually the gas coming out of the balloon, that's quite a good model, because what happens when a star starts to die, the core shrinks, but the outer layer sort of expands, right? And we get that red giant. There we go. I'm going to say that that's my red giant. I'm just going to pretend that all that gas is now a red circle around it, and that's my core. And then what happens? Well, now helium is fusing. Helium particles are fusing into other particles inside the red giant, but eventually, of course, everything has to end. So the helium runs out as well. So the core contracts again, do you remember? And that's when we get our white dwarf. Maybe I can squeeze it this time. So squeeze. We get an incredibly dense white dwarf, which, because the particles have been pushed together, are very hot again. And that white dwarf heats up the gas around it, and that's what a planetary nebula is. I'm so sorry. It's just a hot glowing ball of gas around a white dwarf. Phew, we made it. Right, what about more massive stars? Let's quickly cover those before we go. So what we've just talked about there, the planetary nebula and the white dwarf, that's stars that are about 80% the size of our sun, up to about 8 times our sun. Be really careful here. This is a good time to say we're talking about mass. So when I keep saying like bigger stars or smaller stars, that's not good physics language, is it? One of the things that mass can mean is like how much stuff something is made of. So something can be made of not very much stuff, but the particles are all very spread out. It could be big, right? Or it could be very, very dense, or the particles could be really close together and it could be small. We're not talking about things that are big and small. We're talking about actually how much stuff is in them. So stars made of about the same amount of stuff as our sun, or maybe 8 times more stuff. This is what happens to them, the shrinky, bready white dwarf. What happens to stars 8 times bigger than our sun? 8 times more massive than our sun. Stars that have 8 times more mass. It's such an important point if you're going to write about this in an exam. Well, more gravity in it, more everything. So they burn hotter and they burn faster. So they live for less time. They only live for hundreds of millions of years instead of billions of years. But they do have an exciting life while they're doing it. So here we go. The beginning of their journey is quite similar. They start as a nebula, and then you've still got a main sequence star. It's just very massive. And then instead of a red giant, you get a red supergiant. A red supergiant is just, I mean, hopefully it's fairly easy to remember, because it's just much bigger than a red giant, and it's brighter. It's more luminous, okay? There you go, that's what I just said. Red supergiants, much bigger and much brighter than red giants, because they've got more mass, right? So they've got a stronger force of gravity. So they keep collapsing, and nuclear fusion begins again. So there's more nuclear fusion in red supergiants. Carbon atoms fuse into oxygen, and those get together with other atoms and fuse into magnesium, all the way up to, here's a periodic table, what's the heaviest element that gets fused in nuclear fusion? It's actually iron. Yeah, iron is a very stable element. So you smash 2 iron particles together, they don't fuse and release energy. That's not what happens. So iron's the heaviest element that you get inside these stars. So how do the other elements get made, eh? Excellent question. Well, the core of the red supergiant collapses really fast. And of course, because we've got a hot collapsy thing, the particles are all close together, a lot of collisions, so it gets extremely hot. And yeah, this bit's brilliant. This will help you remember. So you've got iron particles inside this red supergiant now, talking about stars that are much more massive. You've got iron particles, atoms, so protons and electrons. The supergiant collapses so quickly that the protons and the neutrons get smashed into each other and form, what do I reckon? I'm having some sort of, I don't know what that hair's doing. Let's flick you back over. Form, what do you reckon? Come on, what do you get if you maybe I should have said, if you mash a proton and an electron together, what happens? You get come on physicists, you get a positive thing and a negative thing, you put it together, you get neutrons, which is your clue for what is about to happen next. So we've got a red supergiant this time, just like before. It runs out of fuel, so it collapses. The protons and electrons, I don't think you need to know this for the exam, but they're smashed together and they form neutrons. And these neutrons fall towards each other and then they suddenly stop. And that's when everyone's favourite star stage happens. So you've got neutrons, I think it's just like a few seconds that gravity causes these neutrons to fall towards each other, and then they stop. And what happens when things that are going really fast stop suddenly is you get a shockwave. You get a supernova. Everybody loves supernovas. So supernovas are, I'm not going too fast or too slow. It's always hard to tell. Red supergiants, beg your pardon. Red supergiants that have run out of fuel, so collapsed. Neutrons have formed inside the red supergiant. They've fallen towards each other and suddenly stopped. And then you just get this massive reverberating shockwave of as all those neutrons kind of vibrate into each other, which is what a supernova is. Yeah. The shockwave from a supernova smashing particles together is in fact the only way that gold atoms are formed. It's the only process in life, nature, the universe that has enough energy to form gold atoms. So the gold in a mobile phone in your house or your computer, that's how that happened. Supernovas. You want to see a picture of a supernova? Yeah, you do. This one is called Kepler's supernova because he saw it. Johann Kepler, very famous scientist, saw this supernova in 1604. Sadly, really just before telescopes were invented, so they couldn't look at it that closely at the time. But yeah, they just noticed, Johann Kepler and his fellow humans at the time, suddenly noticed this really new bright star in the sky, and that's what it was. So this is a modern day picture that I think NASA have taken. The bluey green is X-rays, and I want to say the red is infrared, and the yellow is visible light. So what's left after a supernova is if you don't know, you might have heard of them. I've given you a clue. Remember, we've had that red supergiant collapsing, iron atoms getting mushed into each other to form neutrons. So the thing that you have after a supernova is a neutron star, just a very, 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 very dense, squished together ball of neutrons. Like the one in this photo here, this circled is a neutron star at the heart of the Crab Nebula. Thanks, NASA. NASA really doing some heavy lifting in this lesson for me. So, exceptionally massive star. I'm really sorry, we could do a whole separate lesson on black holes, but because this is IGCSE and we're just learning what's on the specification, we're not going to. We're just going to say exceptionally massive stars, stars that are so massive that the neutron star gets pulled on by gravity. It doesn't stop there. They collapse even further to form black holes. And there you have it. This is, in this picture, everything that we talked about and everything that you need to know. It's sort of an infuriating lesson because obviously all of these processes are incredibly complicated, and like I say, you could pick up a lot of marks just by remembering the order of these names. Hopefully I've given you a bit of an idea of what is actually happening to get to each stage. Do you want to do Do you want to do a little quiz? Not a test, because tests aren't nice. Quizzes are great, aren't they? Let's do a short quiz to see how much of that you understood / remember. Yeah? Yeah? Let's do it. That was my battery running low. It's fine. It's still 20%. I've got ages. So, right, going right back then. What happens when a star becomes a red giant? What a brutal question. How are you supposed to remember that? What happens when a star becomes a red giant? So what's going to happen to our sun? Just an average mass star. What's going to happen to it to make it turn into a red giant? Is it A, the core collapses? Is it B, the outer layers expand? Is it C, both those things? Or is it D, neither of those things? What happens for a star to become a red giant? What has to happen? A, the core collapses, B, the outer layers expand, C, both, or D, neither. I'm hoping that you got that it's running out of fuel, yeah? It's hydrogen atoms, hydrogen particles are fusing together inside our star to form helium. When it runs out of hydrogen, it collapses. But at the same time, for reasons which I did not explain, the outer layers expand. So it is both. But if you said the core collapses, I'm happy with that because you actually, hopefully you remembered why. But you just have to remember, I'm really sorry, that other processes mean that the outer layer expands because that's what makes it red, right? Because it's cooler. Here we go, just that picture again. Just do some deep breathing. Refresh yourselves. Okay, next question. Which stars form white dwarfs? Which stars form white dwarfs? Is it A, all of them, B, those with a mass over 8 times more than the sun, or C, those with a mass about the same size as the sun? Which stars form white dwarfs? All of them, those with a mass over 8 times more than the sun, or those with a mass about the same size as the sun? A mass over 8 times more than the... It's not very good English, is it? A mass over 8 times that of the sun. The answer is... it's those with a mass about the same size as the sun. There you go. So white dwarfs are stars that start out about the same size as our sun, like 80% smaller maybe, or 8 times more massive. They become white dwarfs. If they're really massive, then something else happens. You've got those neutrons forming. All right. What's a planetary nebula? What's a planetary nebula? Is it A, a cloud of hydrogen gas from which planets are made? Is it B, a cloud of hydrogen gas from which stars are made? Is it C, the glowing gas surrounding a white dwarf? Or is it D, the glowing gas surrounding a neutron star? I can't tell you, I'm very happy with this question. I think this question is really testing you. What is a planetary nebula? Cloud of hydrogen gas from which planets are made, cloud of hydrogen gas from which stars are made, the glowing gas surrounding a white dwarf, the glowing gas surrounding a neutron star. The answer is, it's the glowing gas surrounding a white dwarf. So the white dwarf is very small and hot, so it heats up that gas, and that's when you get the thing that's called a planetary nebula for ridiculous reasons. And finally, what decides whether a star becomes a red giant or a red supergiant? What dictates whether a star becomes a red giant or a red supergiant? Is it A, its mass, B, whether it contains gold, or C, whether it contains iron? What is it that decides whether a star becomes a red giant or a red supergiant? Red supergiants being bigger and brighter than red giants. And red supergiants, of course, doomed to die and become neutron stars or black holes. The answer is, hopefully you got this one, its mass. Yeah, just its mass, not how big or small it is, how massive it is. Poof, blooming heck. That was an extremely dense lesson, wasn't it? Extremely well done. If you, I was going to say if you've taken in all that information, I can't imagine anyone took all that in, but extremely well done for getting through this lesson anyway. If you ever find yourself revising for an IGCSE, hopefully there'll be something in there. You'll be like, oh yeah, because of the class, yeah, bread, right. Okay, I'm going to go to my Facebook page. That is the end of the lesson, and see if anyone has said hello to me, because no comments on YouTube. but there are comments on Facebook. So, oh, you found me again. It's just Tiger and Bird again. Splendid. Good. Thank you, Tiger and Bird. Your comment was incredibly useful this time. Brilliant. All right, it's just Tiger and Bird. Well, hello, Tiger and Bird, and everyone else who is skulking, lurking in the background. Thank you so much for coming. If you want to support me, you can. These lessons take ages to plan. The printouts take ages to design. And there's even a homework and further reading PDF on my website. If you go to my website, every GCSE lesson, IGCSE physics lesson I've ever taught is on my website with the printouts, and there's a massive document on the front cover of the IGCSE page where I've just spent ages gathering together past paper questions and like further reading and different websites that I think would be useful for you after that lesson. So I'm going to update that again this week to give you even more reading and past paper questions. And if you're thinking, wow, that's an awful lot of work, Lara deserves £5 a month, then go to my About section on YouTube and click the button to the website called Coffee and sign up. Sign up now. Do it now. And I will send you Theatre of Science magazine. Theatre of Science magazine is the only thing that my supporters get that not everyone gets, because I just want to be really inclusive, right? I want everyone to be in the science lines. IGCSE physics is hard enough as it is without you having to be able to afford lessons. So everything's free. But if you sign up to support me, I'll send you Theatre of Science magazine. It's extremely good. It's genuinely for all ages and levels. I'm trained to teach physics, and I really don't know anything that is in Theatre of Science magazine before I start researching it. So this one's all about acids. It's got a beautiful choose your own adventure about acids. You go back in time and your knowledge of acids will decide whether you get free again. And there's a which acidic object are you quiz. There's a beautiful, quite in-depth comic about acid rain and how it forms. There's some activities. Yeah, it's like everything I do really. It's kind of designed to be accessible, but the science in it generally goes up to a much higher level than you would get, dare I say, from other science magazines. Yeah, and I send you some sweets so that you can eat some acidic sweets and learn about why acidic things taste sour. And I'll send you some litmus papers as well, so you can test these stuff in your house and just see if it's acidic or not. Right. Oh, and actually, I don't usually advertise this, but there's also from Origami Tree for NASA. I did not design it, but I've printed it on some nice card for you so that you can build the James Webb Telescope and learn about how incredibly tenuously linked it is to acids. So there you go. Right. Thank you so much for joining me. I'm going to go and start planning for next week and putting your homework PDF together. I will see you next week. Only 2 weeks left. Count them. 2 weeks left until the summer holidays. So we've got Redshift next week. Redshift, how we found out that all the galaxy is expanding, and then the universe is expanding. Everything's expanding, and then the last week we'll do the Big Bang, evidence for the Big Bang.